All right, so example number 2 for angular momentum, we have figure 11-14a shows a freeze frame of a 0.5 kilogram particle moving along a straight line with a position vector given by r equals -2t squared minus t I hat plus 5j hat, with r in meters and t in seconds starting at t equals 0. The position vector points from the origin to the particle. In unit vector notation, find expressions for the angular momentum of the particle and torque acting on the particle, both with respect to or about the origin. Justify their algebraic signs in terms of the particle's motion. So first and foremost, we have to think about what our equation for angular momentum is. So we know that angular momentum, L, is r cross p. Here, of course, we're given the mass of the particle. It's 5.5 kilograms. And we're also given the position vector. So we can see that r, that's going to come in with the position vector. But of course, p, our momentum, linear momentum, we need to break that down into mass times velocity. So what we get here is L is equal to mass times the quantity r cross v, like that. So we know mass, we know the position vector r in unit vector notation, and then in order to get to the velocity vector v from our position vector r, we need to derive that equation. So, or take the derivative is what I mean. So r here is our -2t squared minus t I hat plus 5j hat. And then in order to find the velocity vector, that's just going to be the derivative of this first equation. And so what we end up getting is a -4t minus 1 I hat plus 0 j hat. So that's what we end up getting for our velocity vector. Now, here we have a cross product. So remember that crazy equation that we learned when we learned about cross product, we're actually going to be using that again. So that crazy equation was our A cross B, and that is equal to our A y B z minus B y A z. I'm gonna write that smaller. A z I hat plus our A z B x minus B z A x j hat plus, let me zoom in a little bit, plus our AXBY minus BXAY k hat. Okay. Now, when we apply this to our r cross v for our angular momentum equals m times r cross v, r becomes a and v is going to be our b. So we can see here that we only have a x component of our velocity, which is our b vector, and we have both an x and a y component of our position vector. Okay, so we have an ax and an ay. So there's no z components is what I'm trying to say. And so since there's no z components, both this whole term here becomes 0 and this whole term here becomes 0, because again, all of these z's are just 0 because there's no z component of those two vectors. So because of that, we can just cancel those things out, and then we can concentrate on this last thing right here. So what we end up getting here is our r cross, and let me do this in black, our r cross v is going to end up being rx b, no, not b, sorry, vy minus vx ry k hat. So plugging in our stuff here, what we get, r cross b, is going to be rx, which is this whole thing right here. Let me do this in a different color so it's a little bit easier to see. So we get rx, which is here, -2t squared minus t. So rx times Vy, which we can see there's no V component of the, or no Y component of the V vector. So that just ends up being 0. So that's just going to be times 0 minus Vx, which is this whole thing right here. So we get negative 4t minus 1 times Ry, which we'll do in red, which is this 5 right here. So Ry, 5. And then all that k hat. Okay, so the first term ends up being 0. We get R cross V equals 0 minus, and then this is just going to be a negative 5 times 4 is 20 t minus 5. So if I distribute that negative there, I just get positive and positive, distributing that negative k hat. So we end up getting R cross V equals 20t plus 5 k hat. Now, with this, we now know that we also need to multiply this by m, because we know that we're finding the angular acceleration, or sorry, the angular momentum. We're not finding r cross v. That's just a part of our angular momentum. So remember, angular momentum is m times r cross v. So here what we're going to do now is we're going to multiply by m, which was that 0.5 kilograms. So multiplying by m, we get 0.5 kilograms times 20t plus 5 and all that k hat. So multiplying everything by 0.5, we get that our angular momentum vector is equal to 10t plus 2.5. And then our units for that are kilograms times meters squared over seconds. And our direction is k hat. So that is our answer for our angular momentum. And then it said we also want to find torque, right? So this, in unit vector notation, find expressions for the angular momentum L of the particle and the torque acting on the particle, both with respect to or about the origin. Justify their algebraic signs in terms of the particle's motion. Now, justifying this algebraic sign, it's always going to be positive, and we can see that that particle is moving to the left here, and that just means it's not going to be changing direction there, and so we are going to have a positive angular momentum about the origin because that is a counterclockwise direction. If we used our right hand rule, it would be coming out of the page for our angular momentum. Now for torque, we know that torque is equal to the derivative of the angular momentum with respect to time. Okay, so you should have seen that in your notes. So what we're going to do is we're going to take this equation and take the derivative of it. What we end up getting is just 10. Okay, so torque ends up being 10 kilograms times meters squared per second squared, because of course we're dividing by seconds again. But of course, we know the units for torque are newtons times meters. So 10 Newton times meter, and then that's also in the same direction, so it's going to be k hat as well. And again, positive torque means counterclockwise direction. So that sign is justified.